jump to the next thing here. Let me give you a little bit of context to this conversation before I throw it over to Hunter. Hunter's going to get on from JKI. If you look in the requirements from 800-171, there is this requirement, which is pretty vague. And again, 800-171 is very vague. Monitor and scan for vulnerabilities in the system periodically, and when new vulnerabilities affecting the system are identified. That's easy enough. If you look at the detailed paragraph underneath it that kind of describes what this means, it throws out a couple of terms, and one of those terms is perform static code analysis. And static code analysis, there's a lot of tools that are out there that perform static code analysis. I just did a quick search and I found all of these. Coverity is a pretty big one. What's the other one that's really big? I think Vericode's kind of big. Some of these are pretty expensive, $20,000, $30,000 for a license. But they all have one thing in common. Can you guess what that one thing in common is? They don't work with LabVIEW. And that is very frustrating for all of us that try to get anything done with LabVIEW as our primary tool. And so that is causing us a lot of grief. When your IT team comes to you and says, hey, if you're going to release that code, have you done static code analysis? And a good static code analysis tool will go through and it will do kind of an analysis and looking to see, tying into public databases, what are the vulnerabilities. At NI Connect, JKI, Hunter Smith, gave a great presentation on how do you develop robust rocket test software. And he was talking specifically about an application that they developed to meet certain NASA requirements that they could deliver to NASA. And in that, they talked about how you make the interface to meet their requirements. That was really good. They talked about all the requirements documents that come into play. And they talked about performing code reviews. And when Hunter presented this, I said, wait a second. This is maybe a way that we can address the static code stuff. And so I asked him, how did you do your code reviews? And Hunter had a great response to that, which is basically that he built his own thing. And so I'm not going to steal too much more thunder, but I'm going to let you go take it from here and kind of go. But this is why we invited Hunter, is because this is kind of a deeper dive into one of the topics that came up during his NI Connect presentation on how you developed good, robust, high-quality software.
Great.
So,
Thanks,
Hunter,
Steve.
do you have
Awesome.
a presentation?
Yeah, I can share my screen and I can take it over for a bit.
If you guys know JKI, they're a great company. They're a LabVIEW partner of ours, been a partner for a very long time. They actually created the first NI, we didn't call it package manager, but the NI, what would you guys call it?
VI.
Oh, the VI package manager, yes. VI package manager. We liked that so much we bought it from JKI and turned it into NI package manager. A lot of tools actually inside of LabVIEW come from JKI. Great company. So
yeah. Thanks, Steve. So yeah, as Steve said, this he asked me to present this kind of as a extension of some of the stuff I presented at NI Connect. And so what I did is I actually took a lot of the slides from NI Connect, and what I'm about to share has a little bit of slides in common. I know I see a few of you who were there, but I've added a ton of new content specifically around static analysis and security. So I do want to kind of tell you the whole story of developing code in a way that is, NASA grade, as we say. But I also want to open it up for discussion. And so especially when we get to static analysis, I definitely will prompt some questions that we can either put in the chat or people can chime in. As Steve mentioned in the beginning, we definitely want to make this a little bit interactive. So to start off, just to introduce myself, I'm Hunter Smith. I worked at NI for 6 years on their K-12 teams and AE teams. I got to work with things like First Robotics and Lego Mindstorms, and you may have heard of my YouTube channel, Waterloo Labs, where we did wacky projects with LabVIEW. I spent 7 years at SpaceX working on their LabVIEW teams for rocket engine test, as well as the mission control, Falcon mission control system. And then for the last 3 years, I've been at JKI and getting to work with a huge variety of customers across a lot of industries. As Steve mentioned, JKI has been around the LabVIEW world for over 20 years. A lot of you may know us as the VI Package Manager Company. A lot of you may know us as the Jim Kring Company. Our CEO is pretty prolific out there. He got to get up on the NI Connect stage this year. But we've been working with a lot of industries from, semiconductor and, but specifically over the last few years, a lot more aerospace companies. We are starting to take on projects for a lot of these that require a lot of assurance and paperwork, including a lot of companies we aren't allowed to talk about. Bonus points if you can figure out the fake logos I put under there. But the project that we are allowed to talk about is working with NASA Ames on the ArcJet facility. So the ArcJet facility is where they test heat shield components and other high thermal systems, thermophysics, where they blast them with plasma, and just in case the plasma is not hot enough, they then shoot it with a laser just to boost that temperature. And so in order to start on this project, we first had to start by defining how we were going to build our process, a process that is, quote unquote, NASA grade. And yeah, I am not trying to introduce yet another standard here, but NASA grade is just a metaphor. Don't get too excited. So normally when we work with a company, if JKI gets brought in, we're going to write a optical tomography system, or we're going to build a semiconductor inspection system. We kind of just have to define three things. What hardware are you working with? What does the process look like? And then how do you want to interact with it? Whether that's screens or logs or data files. And a lot of times we can have a 1-hour meeting with a customer, write a 1-page statement of work that kind of outlines this, and then work with them iteratively until it's done. And that kind of low overhead method works really well for certain projects. That, as many of you know, does not work well if you're writing code for some of the 3-letter agencies. So I'm curious if anyone in chat can chime in. Are there any agencies that I didn't include here that you've had to deal with when getting code certified or verified? I'm curious. And yeah, the IT is meant to be IT, as Steve mentioned earlier. Working with IT can sometimes be a real challenge. And then just in case, the bag of money is investors. So we've worked with customers where sometimes the engineers at the company itself just want to do this bare minimum version, and investors will insist. Yeah, Tim pointed out the FAA, great one. I'll add that to the slide for next time. Oh yeah, and the Department of Energy. Thanks, Steve. So depending on who's asking, you now have to come up with a bunch of process and be able to build requirements. My house, my rules. And so if you're developing code in someone else's house, you got to follow their rules. So in our case, we're working on a NASA project, and it all stems from NPR 7150.2c, which is the NASA Software Engineering Handbook, which then references the Software and Safety Standard, which then references the Policy Directive, and then depending on if it's safety critical, you have to use different sections of the Configuration Data Management Plan based on your classification. Don't forget your appendices, and the security analysis, which we'll drill into later. And I know this is probably a pain that many of you have had to deal with. Sometimes just understanding, what do I actually have to turn in? When they were asking before, what does the artifact look like? We'll do that. Now, I was surprised to learn, so we were given the opportunity to take on this project. The first phase of the project was defining how we were going to meet all these requirements. And so we had to spend a great deal of time combing and reading through these. And I was surprised that NASA wasn't able to provide examples. I was like, hey, can you give me an example software development plan? And they're like, well, we wouldn't have anything for LabVIEW. And I'm like, oh, that's fine. Give me a C++ one, and I can interpret. And they're like, no, we don't even have that. And in case you didn't miss, halfway through this slide, that 2C changed to a 2D, because that did get revved halfway through. And so we found that we were having to break a lot of ground. We had to define a new process built around LabVIEW, which is, a combo breaker from what a lot of these agencies are used to. But I was also surprised that there wasn't a lot of examples, at least none that were publicly available. So as a part of the first phase of the project, we wrote a software development plan that covered a lot of the software engineering requirements, as well as the security policies. This is a signed and tracked document that becomes, contractually binding, where, we cover a broad range of topics, from project management to, development standards and verification validation, and define that process. And then throughout it, we're expected to be able to prove that we're following this, and document that we're following this, and produce a lot of government records to make sure we're doing it. Now, in order to write that SDP and verify that we were covering all 109 of the software engineering requirements and security weaknesses, we actually had a process. And so this is just a little flow diagram. You can see I have 2 Python scripts, they're in blue. The source for our document itself uses RST, a restructured text, which is kind of like a markdown file. And specifically, this build created the requirements map document. The requirements map was able to then say, yep, here's the section where this specific requirement was linked. And, you know, a lot of times when you're understanding these requirements, it can be tricky. This is my favorite one, that the project manager shall implement the software design into software code. And so it's like, what do I point to that shows that I did that? Look. So, you know, all that to say, a lot of these require a lot of interpretation, a lot of, you know, I think this one's probably the vaguest. But we now had a document that showed here's how we're going to do that. We were really pleased with how it came out. Because we were using a system called Sphinx, we were able to have an HTML, and so this made it really handy for you know, litigation, where they'll say, well, hey, you technically did this. Well, we technically said we would do this, and you know, whether that's in a code review or when we're working with our NASA oversight team. So we now have an SDP. I do want to mention two things about issue and requirements tracking. So I don't think JKI has any, I don't think we're, you know, better at everyone else than issue tracking. I'm sure a lot of you use a lot of these different tools, you know, Jira or Monday to track it. I do want to ask the audience, how many of you feel like you spend more time in your ticket system than you do in your IDE? That can be a challenge, you know, finding that Goldilocks level of effort where, you know, if I have 2 developers and 3 stakeholders, like maybe I update it once a week, maybe I don't need every single transition to be, you know, maybe I can do bigger tickets that kind of lump stuff together. But if I have a ton of users and I have 50 developers and NASA's or the DoD is kind of hovering over looking at tickets, maybe, you know, now I'm going to be spending 50-50. And so finding that balance is tricky. And, you know, JKI is constantly needing to adapt depending on our customers. Some customers say like, hey, just send me an email once a month that says what happened, and others want to have, you know, step by step. So, you know, it does take time to dial that in, and it's something that throughout this process, you know, we probably spent a little more than we needed to up front, and then over time figured out what are the things that actually we should prioritize updating and keeping up to date. And then requirements tracking. So in addition to all of those, we have the specific requirements for our project that are the, you know, you can connect to this device at this rate and read this data with this timing information. And so we had to build out a whole system to track, you know, several hundred specific requirements, and then create verification plans that would say, okay, you know, some rules you have to verify through inspection, or you can verify through unit test. A lot of them, especially if it involves user interfaces, you kind of need to write a manual test procedure. There are ways to automate UI testing, but it is very time consuming. And so, you know, you're constantly finding those balances. And then, you know, we present this as, we kind of nominate these to our customer and say, here's how we think we've proven this. And then they have to agree. All right. So we now have a process outline. We have kind of our basic workflow, but now we actually need to start, you know, creating our tools and making sure that we can follow all these and document it. The first thing we had to do is really refine our coding standard. A lot of the security rules we'll find that can be addressed with good coding. Now, you know, at JKI, we know not to create infinite loops, and we know to create good error handling. And so some of those things we just had to kind of write down and document that these are things that we kind of know intuitively, but it was surprisingly difficult to come up with what I'm calling directives. So, you know, there are things that you should never do in LabVIEW, things that the principles that you should generally do, but, you know, there's exceptions. There's greens that are just like, well, you know, I like doing it this way. And then tip is just kind of well, you aligned it to the left, and I like to align it to the right. And we sat down with our team and said, you know, what's one directive that we can agree on that you should never do in LabVIEW? And the one we came up with was you shouldn't dereference a DVR created in a class outside of that class. Beyond that, it was hard to come up with any hard and fast rule. But you can come up with principles and designs. There even is an exception for creating infinite loops sometimes. And so you do have to find, you know, let's lay out the rules. Let's, you know, get it written down. If it's not written down, then it's just kind of code smell and code feels. And so getting it documented is a good step there. And then how do you actually make sure that that's being used? And that's through code review. So by show of hands, how many of you have code review process for LabVIEW code. Are many of you using that? Are you using pull requests or using? All right, we got a couple hands. I am continually surprised. There are a lot of companies and even high-end LabVIEW users who don't do any code reviews or who do very, very limited code reviews. And even for some of our NASA oversight, I was asking them, how do you normally do code reviews? And sometimes it's, well, we throw the code up on a projector and have a meeting, and it's like that's one way to do a code review. So for our case, we're using Bitbucket, and that way we can go in and comment on individual VIs. We use a lot of screenshots to do it in LabVIEW. None of the review tools are well optimized for LabVIEW at this point. You can see here this binary file. LabVIEW is not able to tell me, and it sure would be great if it could. I have been working with people like Christina Rogers, and I know that her team has been working on some improvements to the diff, the LabVIEW diff tools, and that's something that I would love to find a way to integrate so that it can identify which VIs only had an icon change or a simple property, and as opposed to code changes. So we use this code review to make sure we're following all the processes, make sure the style's good, and provide feedback and catch bugs. One of the things that's been helpful for us in that black box down at the bottom is to kind of call out specific comments. So you have nitpicks that are like, hey, this is something I would have done, but I won't block the review if you just say, nah, you can dismiss a nit with a nah. Discussion are just like, let's talk about it before we do. Scope, sometimes you're like, hey, while reviewing this, I noticed this other problem. Should we bring that into scope and fix it now? Should we spin off a ticket? And last is code golf. How many of you are familiar with the term code golf? So this was a term I learned at SpaceX where I witnessed a lot of code golfing. But that's when, here's my algorithm to sort a bunch of files by file name, excluding these directories. And, it uses 12 nodes. And you go, oh, yeah, well, I could do it with 11 nodes and one fewer for loop. And sometimes that is a useful and fruitful discussion, and most of the time it's not. If we're talking about high-performance loop code, maybe shaving off a few microseconds is worth it. And so sometimes you just have to say, yep, are we code golfing? And code golfing can be a fun sport, but can be an expensive endeavor if you dig into it. So, okay, so now we have a development standard. We have a code review. We need unit testing. So again, by show of hands, how many of you have LabVIEW unit testing stood up or used as part of your system? All right, slightly fewer than had code reviews. I see Darren's hand. That always makes me happy. Thanks, Darren. So I want to briefly just talk about unit tests for those of you who haven't dug into this as much. So here I'm using Karaya, which is a unit testing framework that JKI made. It is free. And so here we can define simple behaviors. I'm testing a function that converts a string to a double, and I want to make sure this pi-like number gets converted to this pi-like value. I want to make sure this invalid string is converted into the not a number, and that correctly errors. And I can build really simple tests. And now if I have a requirement that I can parse strings or that I have strict validation, I have a way of repeatedly verifying that. And it also gives me the flexibility to go in, and if I need to change the functionality of that some VI, I can do it without breaking any of the previously promised interface. But yeah, the way a Karaya test works, you don't have to create a bunch of classes or frameworks. You literally just define a test with a name. Here I have a name, but usually I just let the VI name speak for it. And then you define assertions that need to be true or equal to pass, and then you get out a nice test result. All right, we're almost to static analysis. Talk a little bit more about unit testing. So we can have our very low-level unit tests that are testing a single VI or a single interface, and those are useful when the logic is complex or there's a lot of corner cases like converting strings to doubles. As you build up your system, you want to have kind of subsystem level testing, and so this means now we might be interacting with classes or with objects and doing many operations, trying to emulate what is going to happen in real life. But for instance, doing things like injecting errors, where here I've tried to add a conflicting scalar, and I'm verifying that I get out a specific error code. I also like building in performance metrics into my unit test. Here I'm using an inline timer to measure how long it takes to save my file, and then I can record that in Karaya so that I can compare it. All right, last thing about unit testing is code coverage. So how many of you are familiar with the concept of code coverage? All right, a couple. So in a lot of other languages, code coverage you kind of get for free. If you're doing unit tests, you get that for free. Here's an example in C++ where the green lines have been executed, the orange branches have been executed, the red ones haven't. And so you can see whether it's, oh, you never got into this for loop, or whether it's you never executed the false value of this select statement. You can get a lot of detail. We don't have that in LabVIEW. At least not quite the same. There is a built-in LabVIEW code coverage utility that's part of VIA or part of the unit test framework that you can ask, and you can say, hey, what percent of this diagram was executed? Now, it won't go into the diagrams and, for instance, that select statement, but we can at least make sure we're both cases or all 3 cases or all 12 cases of my VI executed. The percentages are a little bit of a squishy, and unfortunately it won't tell you which cases weren't executed. It just gives you one number per file. But that does give us a way to holistically see how our coverage is changing over time. And so our Karaya test framework then runs NCI. Here it is in Bitbucket, and we can see, hey, we tested 110 different tests were discovered with 1774 different test assertions, and we can see that 24.85% of the code paths were covered doing a simple mean. So that lets us get some kind of metric. All right, last 2 things, and then we're going to dive into static analysis. We also want to have integration testing. So we did subsystem testing where we're testing something small in a box, but now we want to start putting all our subsystems together and really test it as lifelike as we can. So we created something called TIE, the test integration engine, which allows us to do these injections. So unlike the Karaya tests that can run standalone, these require a framework to inject objects with certain states and certain dependencies, but then allow us to write really repeatable tests that are now, I can run several different modes. I can have a test client run against a controller exe, and now I can have a very high fidelity test to prove to my customers how I'm doing it. And then the last test is, of course, the HIL testing. We're not just simulating it. We're running it on real hardware. We're working with real voltages. We might have some loopbacks. We might have a secondary system that's injecting voltages, but now we can, get as high fidelity as we can. In the aerospace industry, we talk a lot about test like you fly. The closer you can get to that, the better you can know, because there are a lot of things, especially in the aerospace world, that you can't test. I don't have a zero gravity generator to test my fairing separation, so there's things I can test. In the software world, kind of unit test is on the lowest end. We're just measuring the lowest level fidelity. Developer tests can have a huge range here. I've just kind of picked, you're doing these small tests, but you may be forgetting corner cases, but you can kind of do it a little more realistic. Integration tests, now we're testing things together. Now we can find bugs that exist between systems. HIL testing, now we have real hardware. Now we can talk about performance and bandwidth and data limitations and write speeds, and then of course flight is the end all be all. But the challenge here is that every time you move to the right, it adds a ton of cost, complexity, and overhead. Writing a small unit test is easy. My string to double one doesn't need to be updated. It generally works. I covered the cases. Maybe if I find a bug, I'll update it. If you have an integration test, every time you change your config format or change your network communication or change your API, you're going to have to update those. And so they become pretty high. These are very valuable, but they're pretty high maintenance. So what we want to do is come in here and add static analysis. So static analysis is on the lowest level. Doing static analysis is not flight-like at all. I can't decide if my rocket's going to fly based on static analysis, but I can catch a lot of problems that are going to blow up my rocket anyway. So let's talk about static analysis. So how many of you have used some kind of static analysis tool in some kind of code language? Only a few, okay. And then I'm imagining if we say how many of you have used a LabVIEW static analysis tool, it may be even fewer. So I'm sure many of you know about VI Analyzer. NI is kind of built-in static analysis tool. I've used VI Analyzer a little bit, but found that it couldn't always, the signal to noise ratio is pretty high, and I couldn't make it specialized. So we created I created a static analysis tool just for us to use internally. And so what we're going to do is open up every single VI, but in addition to, I believe VI Analyzer only does VIs and controls. This one does classes and libraries and a few other projects and a few other things as well. But we want to catch those mistakes. We want to enforce standards. So let's talk about the different tests we can do. Okay, so it's Monday morning. You're coming in. Everyone's been working on the repo. I go to open my project and I'm greeted by one of these. I'm sure it's happened to all of us because the intern added something on their desktop and then forgot to add it to the repo, and it hashtag works on my machine. But when I download it, now it doesn't work, or something got mislinked, and I'm going to sit here and search forever. It is a looping GIF in case this is making any of you anxious. So we started off with a very simple set of rules. So the first one I'm going to call the state rule. So is it broken? That one's the simplest rule. That catches this problem. In addition to reporting if it's broken, our rule will tell you if it has missing dependencies, if it's an orphan, where it gives that error that says this VI claims to be a member of blah, 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 but that does not claim it. Broken, and then lib hierarchy, where we can make sure all class members are under their owner in the folder tree. And so whether it's a library or a class, we don't want class A's member to be in the class B directory, which sometimes happens, especially if you're moving those around. So broken and lib hierarchy are two of our most useful rules. Broken is by far the most useful. When you forget to add something to the repo, when you forget to update something, when you didn't realize you updated a sub VI and forgot it was used in a corner of the code that you never open or is not in memory when you load your project, this catches it. We also do simple metrics: code complexity, size on disk, VI size. These don't pass or fail, but it gives us some useful information. We may enforce certain properties. In our project, we want everything to have separated compiled code. We prefer debugging to be on by default, and then automatic error handling to be off by default. And then finally, style, which is kind of the trickiest one, because now we're talking about things that are a little harder to enforce and a little harder to do. I tried to forward a rule called file name with no white space because I didn't want to have any white space in file names. But because we have a heritage repo, some of our repo obeys that, some of it doesn't, and you have to be able to work with that. All right, let's drill a little deeper into style. So earlier we talked about developing a coding standard, these directive principles, guidelines, and tips. And so let's look at 3 examples of how you might try to enforce a style rule and why. So the first one is a purely cosmetic style nitpick that I've seen certain developers very passionate about. I love that Tim already called out Tom McClellan in the chat. This was something that Tom was passionate about, but had full support from Fabiola, so we know it has some good backers. So some developers really want their errors to be underneath all other things. They want the Z order to be underneath. This is purely cosmetic. It does not impact the code. But if I want to enforce this, I can. I can go in and say, make sure the error wires are behind everything. And if not, I can actually automate that and set it. That one's fairly easy to script, though you do have to do a little work to figure out Z order, because you can tell if they're the furthest back things, but you can't tell if you have to do a little work to figure out if they're behind other things. Okay, so that one's not too hard. Now let's look at example B. So here's a design pattern that I want to say, please don't use. Can anyone spot the potential bug of using this design pattern on B? Anyone see it? All right, and that is that this one, if you get an empty path array, as Tim called out in chat, you'll drop your incoming error. And so if you're doing this, you should probably be passing your error around or have a case structure or something. But as you can imagine, scripting this one is a lot trickier. You look for for loops that have one input error terminal and one output array terminal, and you flag it, and you have to go look, and you go, oh no, this case is actually legit. I can see it branching around, or it has a case structure, or I don't pass in an error there, or it's an uninitialized shift register. There's 100 reasons. And so some of those style rules become really tricky. And then the same thing is true of example C, where here we're saying, okay, for our repo, if you're going to use errors in a for loop, just always do a shift register. I don't care if it spins around a bunch of times. I just want to always guarantee I won't drop my incoming error. And so I could enforce that, but enforcing that as a dumb rule is tricky. And then, I have to write scripts to do these. How to identify common failures, and how do I flag legitimate exceptions? And so, I'm asking these questions. We've created a lot of tools at JKI to audit for some of these, but, it's not easy, and I won't claim it's a solved problem. So really, I just wanted to kind of throw out some of these examples to get you thinking. And in a minute, I'll ask what style rules you would want to enforce. All right, let's dive a little deeper into security now. So when we were working on the NASA project, we were directed to the CWEs. How many of you are familiar with the CWEs? So common weakness enumerations is a open source a community list of vulnerabilities. And so if we look at the latest version of the list, we can go down to and see the top 25, and it will identify common software failure modes, incorrect authorization, out of bounds read, where you're reading out of bounds on memory. Now this database has hundreds of different weaknesses. And in our case, our customer identified a set of 38 or however many this was, 28, excuse me, for us to identify. Now, some of these in a LabVIEW world are very interesting. So for instance, use of an uninitialized variable. I generally think, in languages like C and C++, where, if you create a memory, if you create some new memory, you may just get whatever junk is in there ahead of time. Now in LabVIEW is a memory managed language, and so in the same way, you can't quite get the same vulnerabilities. Now, there are a few ways. There are a few low-level memory access tools in LabVIEW, and so for that one, we may say, okay, in general, LabVIEW is not vulnerable to this because there's not really a way to get an uninitialized variable unless you're doing pointer math, and the only pointer math we do is in this sub-VI, and here's how we wrote a test to verify that it never uses uninitialized memory. So that's one example. Another one may be something like improper input validation. So this one's a lot broader of basically if your code receives user input, whether that's a string or a number or a file or a path, what do you do to validate that they're not doing something nefarious with that? I can write a test to say, are you using the low-level memory tools? I can't automatically write a test to say, are you properly validating all your inputs? And so it does become tricky to break up these rules that, span network communications and file I/O and memory and sensitive data. So what we did was we took our 28 CWEs and split them into kind of 3 different groups. So some things we can address with development standards. So for instance, input validation or infinite loops, avoid infinite loops. So in there, just as we would with any JKI review, if someone spots an infinite loop or I'm haphazardly passing an input into something, it would be called out. I need to follow these developer standards, and I need to, and that should be called out in code review. Some are basically we just have to write some prose that explains to our customers why this is different in LabVIEW. And so with things about memory, with things about environment, with things about execution or compilers. There are certain things that were, either hidden from us in LabVIEW or done for us in LabVIEW. And I'm sure a lot of you have ran into the challenge that a lot of times when you're trying to do assurance work, you're proving it to people who know nothing about LabVIEW. Maybe they're an expert at some other language. They're a C++ expert, and so they at least know what an integer and a memory failure is. Or maybe, as we've found, a lot of times you're proving this to people who have no software-specific knowledge or only very vague, and so it really becomes about the kind of the prosaic explanation. So let's drill into one in particular that I think we might be able to automate. All right, so this is one of the CWEs, CWE 78, improper neutralization of special elements used in an OS command. As you can see from the picture, some people try to get very clever. This person put a license plate that was an SQL query that if they got automatically scanned by a camera and then that text was OCR'd and then put into a database that it could basically drop the entire table and certainly get them off. Now, what do you think the odds are that there's, a drop table check in the OCR code, or there's a drop table check when they ingest it, or, so there are certainly instances, and I know, with website forms, there's certain times when you can inject a little thing and it'll run some JavaScript and you can do very nefarious things. Now, in LabVIEW, this is not as big of a problem because we very rarely have access to, OS level commands to, be able to read or write files or manipulate memory directly. And so in LabVIEW, because everything's kind of has a box around it, we're largely protected with one notable exception. So that notable exception is the system exec. So system exec just runs a Windows command. So here, for instance, is a sub-VI I wrote that was trying to measure the memory usage of a process, of a task. The original version I had written used the command task list and then passed in, you can filter and say, oh, just give me back the name of the task I care about. But that meant I'm passing a user string into my OS command, and maybe I can say, okay, you can only pass in a command if it matches an existing task, or I could do that. But instead what I decided to do is I'm going to hard code the input to that system exec, and then I'm going to filter the results myself. And now I'm protected. And so I have security checklist number 4, which is the one related to OS commands. I can now use crawler to go identify every place where the system exec is used, and then I can manually audit each one. So if I can verify through scripting, I can verify, hey, this system exec has a string constant in, check, that one passes my check. This one maybe does some string manipulation, and so then I would have to go and do a manual audit and say, how is this string being manipulated? Now, in our code base, we only have, out of our thousands of VIs, there's maybe 3 or 4 instances where we're doing this, and so that one's fairly easy to draw a box around. But it does get trickier with these other ones. So for instance, file I/O, there's a lot of security requirements around guarding file I/O, making sure temporary files are closed. Okay, maybe I can go through and crawl, and just yesterday, I'm working on a new security check for crawler that will go and find any VI that calls any of the things on the file I/O palette, plus some of the OpenG file I/O, plus some of the other things I know about. And maybe I can't put a comprehensive list together of every single VI that you could possibly use to interact with files, but I can at least identify all of them and make sure they show up. I made a list of, here's all the files that I expect my application to interact with, and then here's all the VIs that are doing file I/O, and then I can check those and say, yep, I forgot about this file that we're touching, this temporary file, or, I didn't realize that was actually opened in 4 different places. So, okay, OS commands is pretty easy to find sysexecs. File I/O is a little trickier. There's a bigger list of file I/O commands. Network communication, again, I can find all VIs that call TCP or call that call network streams or that call shared variables. But it's kind of impossible to make a complete comprehensive list. But again, I can identify those, and I know the ones within my repo. Memory, okay, maybe I can identify the tools that use low-level memory access since there are a relatively few. But then the last 2 checklists here are kind of the nastiest. So authentication, there's not really telltale signs that you're doing authentication. Maybe if you have a terminal called password or a password display. And then the hardest one is sensitive data. And we've had to work really hard with customers to define what is sensitive data, because there's a bunch of security requirements that say if it's sensitive data, you have to handle it this way. And so you say, okay, is the config sensitive? Is the TDMS data sensitive? Is the scaling sensitive? And based on how you define that, you might have to draw boxes. So we're going to use crawler to systematically identify targets where one of these security lists is applicable. Then with some very limited cases, we can automatically automate that, like with this string constant into the sysexec. But in other cases, we just have to flag those and allow you to audit that. But at least it allows you to approach it systematically, where I look through all 5,000 VIs, and sure enough, there's only 4 that have the sysexec, and here's an explanation of those 4. Or I looked at all the file I/O. Now we have 64, I'm making a number up, that do file I/O, some bigger number, and now I might try to apply some systematic checks, or at least do that. One of the other things you can do is create wrappers. And so you say, okay, in our repo, you are not allowed to call open file reference. You have to call open file reference NASA version that adds in 2 extra checks. And now I can, again, with my crawler say, no one's allowed to call open file. If you're going to call it, you have to call my wrapper, which has open file inside of it and does these 2 or 3 things ahead or before. So as the glyph in the bottom says there, this is something that's under development. Throughout the process as we've been developing this code base, we've been using crawler to identify the basic problems as well as start to use it for some of these security things. Some of them are straightforward, some of them are tricky, and in the end, the artifacts are, we're going to create some of these artifacts as tables or lists of files, but then some of them need to be broken down very specifically. All right, so I do want to open it up just a little bit. So we've talked about the basic checks like broken or lib hierarchy. We've talked about the metrics like VI size or code complexity. We've talked about style, which is, one of the trickier and more nuanced, but I know people are very passionate about it. If you're very passionate about style, I recommend you check out my style debate that I had with Tom McQuillan. If you search LabVIEW style debate, you can find that on YouTube where he and I got into some nitty-gritties. And then the security things that a lot of time aren't driven by things that necessarily we want, but maybe assurance we have to provide. So the question to everyone is, how do you get ROI from these rules? Now, if I look at some of the VI Analyzer rules, I think we can all point to some that are very low return. Broken is definitely the most valuable rule. If I don't break production, if I can make it so when I merge my code, it's hard to commit a broken VI. Because it checks, it makes sure, it verifies NCI that nothing's broken before I can merge. If I can catch errors fresh, if I break something in someone else's code, if I get an email the day that I push, as opposed to 2 months later when we're testing it and you go, oh crap, I didn't realize I broke that. And then fast time to fix. So if I get an email that says, hey, these 2 VIs are broken, this VI has the wrong execution setting, and this VI wasn't separated code, then my time to fix is really quick. So, if you can catch things and prevent breaking, if you do break something, you want to do it fresh and you want to do it fast. So with some of the rules I've talked about, thank you, Tim, for linking the presentation. With some of the rules I've talked about, or your suggestions, what are the rules that you, if you could, would enforce on every single VI in your repo? And if you want to unmute yourselves or just chime in here, feel free. We'll try it as an experiment. Anyone got any suggestions? All right, you all have perfect code with no star rules. I get that it's tricky. Yeah,
I do appreciate the CWE thing because that's when you're just trying to check the boxes, that's what you can show people, right?
Yeah.
So there's an ROI that's just we check the boxes. Is that the most valuable thing to your code? Maybe not, because so many of those CWE things are like not relevant to LabVIEW. But I think it's helpful if you can have something you can give them as a piece of paper, say, we did that.
Yeah.
Now, if you're going to go through the effort of doing a check anyway, might as well look for things that actually help you. And I think the broken code thing is interesting. Memory leaks, those kinds of things are also very helpful to you as a LabVIEW developer to make sure you don't have to support something later on. But I really appreciate this one. This one actually takes, I think, the most work because you have to go and understand that and figure out how to apply it back into LabVIEW. So it's probably the hardest to implement in the tool.
Yeah, no, exactly right. And in our case, the 28 on this list were defined by our customer. And so, they defined that list and then we had to go and break that down. There are hundreds of CWEs. They could have picked any subset. We could have suggested some to add or some that were irrelevant. But as Steve said, a lot of these are incredibly vague, like input validation or, resource management, where, are just race conditions like, okay, gotcha, I won't have race conditions. But yeah, through a systematic approach, you can address each.
There's a good question here about, and we even talked about doing this with VI Analyzer and just writing some additional capability into VI Analyzer, maybe just with custom tests. So why did you go down a completely separate route from VI Analyzer rather than going down that path?
Totally. Great question, and that perfectly leads into my next slide. So in short, yes, you can do this with VI Analyzer. You can certainly write custom rules. Certainly things like broken are built right in. One of the reasons I built it, so this is the user interface for crawler, where I'm going to load in a class I have a set of rules I'm going to run. You can see it's massively parallel, which VI Analyzer is not. It's going to check and identify those, and with certain things, it's going to fix them. So if I get a VI Analyzer result and it says I have 4,212 errors, I'm not going to fix it. Now, certain things you can fix, like separating compiled code, error handling or broken, I can't automatically fix. But I wanted a tool that was both useful in a CI context, in the verification and providing artifacts, as well as in the developer context, where now when CI tells me it fails, I can just open this up, apply those fixes, and then use this tool I can double click on each item and open it up. And what the artifact that this creates is a CSV file. And so this is a CSV file showing that I ran yesterday on our repo. And you can see the rules. Each rule is across the top. Now, not every rule applies to each thing. You can see here there's some classes, and the debugging doesn't apply to classes, but the broken still does. Classes can have broken arrows. And so now I imported the CSV into Excel. I added a little conditional formatting so I get my nice colors, and I made it into a table. So now I can filter by things. And so in the end, I think this can complement VI Analyzer. I don't, there are several VI Analyzer tests that I would love to import into Crawler, and several Crawler tests that I think could port into VI Analyzer. I think they work together. I think one of my challenges with VI Analyzer is I start from that list of here's all the tests you could possibly run, and I like narrowing it down to give me the 5 or 6 that are useful. Can be a little intimidating, admittedly. So yeah, Ryan's question, Crawler is available now. We're working with customers to get this out there. This is something that we used internally. But yeah, we want to get it into your hands. So yeah, let me just finish a few slides and then we'll open it up to discussion. Yeah, so Darren's asking some interesting questions about performance. So yeah, as he mentioned, he and I have a good powwow next week, and I'm going to talk about some of the architecture choices. Crawler is also optimized for CI, that it has a great command line interface. It provides a very simple context. So here, when I run it, it tells me, you have 4,220 VIs. I ran 22,000 checks. Here's the specific failures. And now when I get an email, because this is built into Bitbucket, when it fails, I get an email and it says, yep, these 2 were library misplaced. These 2 you forgot to turn debugging, and this one you forgot to turn separate compiled code. And now I can check, and hit it again, and it runs. And you can see, this took 8 minutes to run my 4,000 VIs. And then the kind of last step is to build it into a full CI system. So now every time I push, I'm going to have a YAML, and this could be true of either GitHub or Bitbucket or GitLab or your system here. Almost all of these, or all 3 of these, have self-hosted Windows runners, where now I have a Windows runner that I have my LabVIEW set up on. It gets a signal from the YAML, and then it's going to run my unit test, my crawler, my builder, my integrations, and then capture all those results and artifacts. All right, I'm going to talk about 2 more things, and then I'm going to try to open it up for discussion. So I do want to address the elephant in the room, and that's AI. And so we talked about how some of these static analysis tests would be very difficult to write. And I can certainly imagine a future where we're using AI to do more of that. It'll probably be a while before we can trust AI and said, hey, AI hallucinated that this repo is totally safe. But maybe we can use it. So JKI is working on some AI experiments right now, not on static analysis yet. But one that is public now is VIPM.io, which is the kind of back end of VI Package Manager that allows you to find and identify packages. Our CEO, Jim, has worked on a new tool where we're now scraping all the VIs for lots of metadata and then using AI to match up an English query with VIs. So you can say, find me a VI that does this, and it will look through everything. This is it's in beta. But yeah, it is public. If you go to VIPM.io, there's a button there where you can say, try the beta. But I can definitely imagine a world where AI is a bigger part of this. We're starting to experiment with that. I know NI is working on a lot of AI tools around understanding code and generating code. And then, we're now adding to the mix by discovering code. All right, the last thing I just want to get my quick plug in. I do want to talk about the tool that we built using this process, and that's our StarGoat tool. So this is a turnkey rocket engine test stand tool where we're going to have a controller that can run on Windows RT, talking to a client, doing DACMX, doing millisecond level sequencing, doing control loops. We make it so our users can configure their interfaces straight in the IDE or in the UI. Add all your DACMX or OPC channels, configure all your scaling, pop out plots. We can do our high level sequencing. Users can customize their diagrams and make it using these no code VIs. And so this means that for a lot of our customers, if they just know what their hardware, they can configure their hardware, they can write a script to do their process, they can do their interface, they can get this out and let JKI take care of a lot of the assurance. So this is actually, I think, yesterday's build, where you can see, the peer review and standards are done, as part of peer review. And so we've already enforced those. We do our static analysis. We do all of our unit tests. We do 3 different types of integration testing. We have 3 different automated builds, and it's all captured, documented in CI. And now every single day, I have a daily build that runs these. And when someone breaks production, we know about it quickly. We do have things that escape, but generally the rule is if you have a bug that escapes production, the first thing you got to do is write a test that would have failed, and write the test before you write the fix. So whether you want JKI's help with a turnkey product like StarGoat or our Test Executive Pegasus, or you want to use some of our tools or just ask for some of our help, we're always excited. You can reach out to me or Treek, and then Steve has been a great ally in a lot of this. We're trying to solve a lot of different problems, and we want to find that. So yeah, I'll open it up to discussion, and we can dive into any specifics.
So there are a couple of questions in here that are good. So one is a little bit about the relationship between security and quality, because a lot of what this is checking for is quality. What VI Analyzer looks for is quality. Mm-hmm. Kind of the question is, why don't you look for security specific stuff? But I think the answer to that is kind of more about how is security related to quality, and are you looking for all the security stuff? So you're not really looking to see is data encrypted. I think that happens at kind of a different level than this. That's not really the static code analysis. It's more of your architectural analysis. Mm-hmm. But give me any thoughts about, how does quality and security relate?
So in the end, static analysis can only test the things that you write it for. As Steve mentioned, there's a lot of other tools out there for C and C++ that have, hundreds of hours or, thousands of hours built into them and to follow common patterns. We don't have that yet. We're working on that at JKI, and we're first working on it for our internal use. But we want to work with you to help identify these. So, when we looked at our list of security things, some of them can only be done with smart developers looking at the code and manually reviewing it. I can't detect every infinite for loop, and I can't tell you if your input validation is sufficient. I don't think we're going to have an automatic test that can do that. But if we have a security policy and says, here's our documentation, here's what we expect you to do, we can do that. The LabVIEW caveats, we just have to explain to our audience. And then the security checklists, it's about having a framework to approach it. If someone says, hey, prove to me that you follow everything, I can't. But if they say, hey, here's 28 specific things, tell me how your code addresses this. And some of these we can use static analysis to make it a little more systematic. If I just say, well, we only write good file IOs at JKI, or we only use network comms that are good, it's like, well, are you sure? There's 4,000 VIs in this repo. Some of them are years old, or have been moved across. And so adding crawler just allows you to make it a little more systematic. So now I have my approach through my explicit list of CWEs, and then I can combine that with my static analysis tools so that at least I can have a systematic approach to creating, to telling that narrative. And, in the end, it is about telling a narrative to our auditors. It's we want the security that benefits us, that gives us good ROI. I don't want to have broken VIs, but a lot of these rules are about how do I explain to an audience that I'd made sure there are no infinite loops.
Kind of gets into what the problem is with security, which is once you start going down the path, you open the door, start doing this, there's no end to how far you can go. And if you look at a lot of these text-based static code analysis tools, they're expensive. They're $20,000, $30,000, $40,000 a year just to have the software. And the reason why it's so expensive is because it does so much. Like they are constantly looking at all the things you can do. Hunter's done a lot here, just one person. That's pretty amazing. He's not going to do everything that could ever be, but I think he's done a really good job here of identifying what the top concerns are for a security auditor that will look at this and being able to go to them and say, have we looked at everything that could ever possibly be done? No. But have we looked at the main things that we know people would attack? Yeah.
And at least I could write a test to know where my loops are. I know how many loops I have and start from there.
Yeah. A lot of other good questions in here. We do need to go kind of the next thing, and I'm going to get kicked out of the room here in just a minute. So I just want to finish with a couple of comments. And then one question that came up under is if you have a link to some more information about Crawler.
We do not yet have a landing page for JCrawler. It is still kind of hot off the presses and in development. I'm going to work with Tariq on my team to get that as soon as we can. But in the meantime, feel free to email me, just hunter@JKI or Tariq, our sales executive at JKI, and we can jump on a call and start having those conversations.